Good afternoon, everybody, and welcome to this informational webinar presented by Cleveland Scott York in conjunction with Tumbleweed. Today, we'll be dealing with the topic of research conducted in microgravity and tackling the technical and legal challenges confronting organizations seeking to take advantage of this emerging field. And I am delighted to welcome to the webinar guest speaker Johanna Sturm, who will be addressing the state of the art in terms of systems for accessing microgravity environments. Johanna is sorry, I beg your pardon, Johanna. I checked that earlier on. Can't believe I made that. Johanna is a founder at Tumbleweed, and Tumbleweed are building the next generation logistics layer for the low Earth orbit economy by radically simplifying the path to space through a revolutionary combination of technology and services. Tumbleweed allow Earthbound industries to leverage the benefits of microgravity without needing specialized space expertise. So Johanna will be giving her presentation first. I will be addressing the intellectual property issues afterwards in a relatively short talk. And then we will be doing a Q&A. So the way we normally do the Q&A, if you go to the chat panel, I think you can put questions in there, and Johanna and I will discuss them together after the conclusion of our presentations. So Johanna, it's a very great pleasure to welcome you, and we've had some interaction before, and I'm very much looking forward to hearing what you have to say.
Yeah, thank you so much. Let me see if I can figure out the screen sharing, but thank you so much for the super warm welcome. Yeah, I'm super pleased to be here and to show you around a little bit of Tumbleweed. I brought a bit of a more general overview for you on like space and what space also brings to Earth. And then also we'll be introducing our platform a little bit. But yeah, maybe to introduce us a little bit first, we're Tumbleweed, and our entire goal that we set ourselves is to make access to space, access to microgravity as easy as mailing a package. And yeah, with that, we're launching our first mission soon. We're sold out. We're oversold out, actually. Yeah, and we're based in Austria and the Netherlands, just building like this bridge to space, so to say. But maybe let's start a little bit in the beginning on like why even go to space, why even care about space. And I brought you some of the images that we usually hear about and what we see that people think of when we think of space. And of course, I mean, there's the cool rockets there, or the Artemis program, like the lunar missions that are always huge. We have the astronauts. We also have the pretty pictures of stars from the Webb telescope and so on. But we also, of course, have this pop culture, this like very future thinking. So if you think of the Starfleet Academy or ET or even Star Wars, or maybe even a more real life example of like these Mars bases, for example, that we've been hearing quite a bit about in the last years. I think space often feels quite disjointed, quite far away, and quite, like a novelty. But in fact, the space economy is kind of already here, and it's expected to grow quite a bit. So yeah, for example, McKinsey here is projecting like a 1.8 trillion global space economy by like in like a decade, even less a little bit. And if you look at this a little bit closer, I don't know if you see my cursor, but you will see that like there's a portion that is the backbone, and there's a portion that's the reach, and this reach is especially growing. With the backbone being more this infrastructure type of thing. So here we have, for example, like the habitats that we just talked about, for example, for a lunar base. But of course, there's also a bit more down to earth type things where you have like satellites in orbit transportation or transportation between orbits, for example. And yeah, that is kind of the backbone side, this infrastructure supporting everything. But the really, really big ticket item, the one that is like really also expected to grow at a higher rate than the global nominal GDP in the next decade, that is the reach, or what is also called downstream. And this is the stuff that touches us every day. Like if we, I'm not figuring out how to go back. Yeah, okay. Yeah, this is the stuff that touches us every day. These are these downstream things and how we use space every day. We have, of course, the Earth observation parts. You'll see that in your weather reports, but you'll also see that for navigation, for example, if you open Google Maps, that is powered by satellites. We also, there's also some super cool applications that you might not have heard of in terms of Earth observation. For example, I met a really cool startup like a week ago that use LiDAR imaging from space and sensors like that to monitor structural and ground motions with like millimeter accuracy just from space. So yeah, obviously there's also the communications part if you think of Starlink and the internet. But yeah, there's also defense that's rising quite a little bit, and there's tourism. But you see, there's like this whole like the space tourism that at the moment is not necessarily for the masses. But you see, kind of there's like this huge like span of things that you could be doing with space. And I think that is the exciting part about it. Now, here we're mostly talking about data exchange, right? Of not necessarily transporting something directly. But we also know another example of in-space research, and that is, of course, the ISS, which is very well known, not just as like this peace project, right? This global like this outstanding example of global collaboration. But there's also like the research part that is going on there, and transitioning towards manufacturing a little bit as well. So yeah, the ISS, it is in low Earth orbit. So that is an orbit that is a lot closer to Earth, where you have microgravity. And that is usually the most important thing about these types of research is that you have microgravity. So imagine you can turn off gravity or kind of turn off gravity, right? You're basically in free fall around the Earth. And that kind of creates a whole new biophysical environment. So, for example, you have no buoyancy, you have no convection, but you also have this hard vacuum. You can use the extreme temperatures. There is radiation environments if you're interested in this. And if we take, for example, just like these no buoyancy and no convection signs here, imagine on Earth when you grow a protein crystal, gravity like pulls heavier molecules down and the convection currents disturb the structure. But in microgravity, because these two are not happening, every molecule stays exactly where chemistry puts it. And so you get these really nice, quiet, uniform crystal growth and cell growth as well. So for example, there's scaffold 3D bioprinting you could do. Yeah, on the other side, there's also some other topics like aging, like processes and changes in cells and tissues are much accelerated in space. So here we're really talking years becoming weeks, with like some estimates are that it's up to 10 times faster. And so we can study age-related diseases. We can do longevity models, but we can also look into organoids and organ-on-chip research, right? And so there's quite a lot of potential, quite a lot of things, and like quite a big opportunity also in terms of monetary value. So yeah, we see the potential is quite vast. To give you a bunch of concrete examples, maybe as well. I know Adrian is going to dive into one later too. But in microgravity, you could, for example, do 10 times faster glass fiber cables, C-line cables. But you could also, for example, a couple of years ago, the first space-grown human meniscus came down from the ISS. So there's quite some potential there. And we went around 2 years ago asking people, hey, do you know of this? And a lot of people came back to us and were like, yes, of course we know of this. But we're not going to do space. You know, this what we just talked about, like this novelty factor. seems extremely hard, takes a lot of time. The launch costs, even though they've gone down so much, are still very high. And most importantly, a lot of them are not space engineers, like aerospace engineers. And so to do this, you kind of had to turn your entire organization into a space company. And to go to the ISS, for example, we saw that there's really more than 700 pages of paperwork that you have to be specialized to fill out. And now if you take that on top of, for example, something like the pharma industry that already has a lot of standards, there's no reason and no financial incentives to do this. And yeah, with this, as well as kind of this limiting factor of not having that much potential to research iteratively, because, well, the launch takes a couple of years and like a lot of money, you're not necessarily going to do this like a bunch of times. We saw that like the barriers are too high, and we decided to tackle that. And yeah, this is where kind of the slogan came from, this making space as easy as mailing a package. And there, yeah, we have two full of innovation. On the one hand, we have our pods, which are kind of like boxes. Payload containers is what we call them, but in reality, they're just boxes, like containers on a container ship, just a bit smaller. And they kind of range from like the CD box size to like a microwave size. And their whole thing is that they're fault isolating. So that means whatever explodes, leaks, whatever inside will stay inside. That is our guarantee. And because of that, we can certify the box, and people don't have to certify their experiments. So that means you save your internal project costs. You don't need to fill out all the paperwork. You don't need to do all the qualification testing to be able to fill out the paperwork. And you just need a lot less aerospace know-how, because inside the box, since the box doesn't is pre-certified, you can build like you would on Earth. And yeah, inside there's also some extras. We have some temperature control and atmospheric control. There is like a little Linux computer in, so you can also send programming up and down and get data down, of course. You get some power and some volume and some electrical energy and some data exchange, of course. And yeah, this is kind of the system that we've established. And then we said, okay, we have these pods. People can go up and down. People can put something in there, but they can't bring the stuff down yet. And what we saw is, especially with a lot of like biological or pharma payloads, this is where it gets most important, right? And so we said, okay, let's just also build a capsule. And that is what we did here with our Oasis capsule. It is a reusable capsule that we're currently building. And here the idea really is to make the process as easy on the user as is possible. So the idea is that instead of having this 2-year timeline, these 300,000 euros of project cost at least, that you just get your pod, like your little container, that you can then build your payload like you would on Earth. You can work with your usual suppliers or like integrate just like you would on Earth, maybe a little bit smaller. Then it goes onto our space container ship on our Oasis. The Oasis is launched, and then it will stay in orbit for a couple of weeks. There is experimentation in orbit. You can, again, send data up and down, and then Oasis comes back to Earth. Your pod is taken out and is brought back to you. So this way, it gets a lot cheaper, it gets a lot easier, and you can build on what you learn. So you can also research iteratively. At least that's the idea. At the moment, we're obviously still a bit earlier. Yeah, so we have a first mission launching in a couple of months. Fingers crossed, and with 4 customers on board. And this really includes research organizations. We have microfluidics experiments on there. We have, yeah, a bunch of lower TRL material studies, but then also some quantum computing digital twin. So really the span is quite big of what you can do up there in microgravity, and the cases for which it's relevant are super interesting, all of them. So yeah, this is kind of the first launch, the first try for just our pods, so it's not coming back yet. And the coming back, the return is what we're going to attempt in early 2028 with Oasis Beta. So here, this will be our first orbital return mission where we really get this full circle around. Now, yeah, the idea is, of course, to scale with the economy. I just showed you the graphs for 2035. And so, yeah, to unlock this scalable production and kind of build this infrastructure. And so, yeah, we're launching soon. I tried to keep it short so that we can learn more also about how to patent in space, what to do with the stuff that we kind of develop on this platform. And yeah, I'm very happy to pass it on to Adrian and looking forward to your questions. I hope everything worked out with the internet as well. I did not check. Yeah.
That was great, Johanna. Thank you very much. Very clear presentation. And I have a number of questions myself. So please, if you do have questions for Johanna, put them in the chat box, which you can see at the bottom of your Zoom screen. So my talk, can you see that? Yeah, it's
Yeah,
up there.
how it works. Yeah.
Yeah. Okay, so my talk follows on from what Johanna was speaking about, and I'm going to be addressing the intellectual property issues in microgravity environments. And for the purposes of this talk, I'm not talking about inventions that are primarily designed on Earth and used in space. I'm going to be dealing with the type of research that would be facilitated by the tumbleweed pods, such as research that is conceived on Earth and conducted in a microgravity environment. So Johanna's set out a number of compelling use cases for microgravity research. And just to recap on what was said, you have a new environment that is not attainable on Earth, and the forces of gravity are considerably lessened. They're not reduced to absolute zero, but they are a tiny fraction of what exists on terrestrial conditions. And this gives rise to results that are not reproducible under the influence of gravity. So, as in the previous talk, the forces such as convection, etc., are almost completely eliminated. And this is a compelling environment for industries such as chemistry, pharmaceuticals, material science, biology, semiconductors, because they can take advantage of these unique conditions. And the costs of sending payloads into space have fallen dramatically over the past 40 years, and they continue to do so thanks to the work, not least of organizations like Tumbleweed. So I would just talk briefly about one example that I think illustrates the potential quite nicely. So this is Keytruda, which is a monoclonal antibody for the treatment of several types of cancer, but lung cancer is the main indication. And monoclonal antibodies are very large peptide structures, and forming crystals on under terrestrial conditions tends to be very challenging. And when Keytruda was first launched, it was delivered via infusion therapy, intravenous infusion therapy, which needed to be repeated very frequently and took up to 2 hours. So protein crystal research was conducted on the International Space Station, which gave insights into a new formulation for subcutaneous injection. So this is much preferable to an intravenous infusion. And this has resulted in a new formulation of Keytruda where the infusion times are less than 30 minutes and it needs to be done once every 3 weeks. So that is a dramatic improvement in patient accessibility to this therapy. It's a very active field for patenting. So I did some quick research on patents mentioning microgravity in the claims abstract or title. And you can see here in the graph that this has grown dramatically over the past 20 years and continues to do so. So the intellectual property issues are numerous, and I'm just going to touch on them in this presentation. And frustratingly for you, the audience, I will be um, not providing many answers to the questions, but at least I will be framing the questions that I think need to be addressed. So, as you might expect, patents being a territorial right, the territoriality of intellectual property in space is a big issue. We don't really have a lot of legal instruments to guide us in how inventions are dealt with in these environments. But what we do have is the Outer Space Treaty and the Liability Convention, which I will briefly outline. There are issues of ownership and inventorship of intellectual property, and the usual questions of patentability also arise. I'm going to deal with contractual IP frameworks for space collaborations, as you can imagine, in such environments where there is a dearth of explicit legal provision, then the contract usually will do the heavy lifting. And I will also touch on non-practicing entities in space, which I can imagine will be a big issue. So I'm assuming that people in the audience know a little bit about patents, but just to refresh your memory, patents are territorial rights granted by a sovereign state in return for full disclosure of an invention. And they are generally only enforceable within the jurisdiction that grants them. So space is governed by a few international treaties rather than national boundaries. And this creates legal uncertainty about issues such as infringement, the jurisdiction that applies, and whether a spacecraft counts as the territory of its state of registration. So we'll have a look to see where we might obtain some guidance on answering these questions. So we do have some analogues, and a good analogous situation is the maritime environment. So in the UK, a patent is in force within the islands of the United Kingdom and up to and including the continental waters. But in international waters, it does not apply. So this situation has been examined by the Federal Circuit in the US, and they have reasoned that patent laws extend to the decks of American vessels on the high seas. And interestingly, in that decision, the Federal Circuit noted the reasoning would also apply to manufacturing machinery on spacecraft. So I think you can see that the comparison between international marine situation and the low Earth orbit situation is quite relevant. A solution to the legal gap would be to make patent law enforceable for objects in space that come under the jurisdiction and control of a given country. And this has been undertaken by the US in the Patents in Space Act. So it states that any invention made, used, or sold in outer space on board a spacecraft that is under the jurisdiction or control of the USA is considered to be made, used, or sold on US territory, except where an international agreement has been concluded that states otherwise. And as far as I am aware, although maybe members of the audience will correct me, only the USA and Germany have such provisions. And up until the availability of platforms such as the one provided by Tumbleweed, a lot of research was conducted on the International Space Station, which still continues to be the case, and that is governed by an agreement between the participating nations. So the main legal instrument that we have, which gives us some guidance about territoriality, is the Outer Space Treaty. And this establishes that states retain jurisdiction and control over objects launched into space. It is silent about intellectual property rights, but we at least understand that the jurisdiction is retained over from the launching country. So there is a quasi-territorial link between a spacecraft and the intellectual property laws that apply on board. However, a lot of ambiguity remains for multinational missions, private space stations, private platforms, and commercial platforms operating in mixed jurisdictional environments. Thinking about the issues that might arise, I will talk now about inventorship and ownership. These are obviously key issues in patent law. All rights tend to flow from the inventor, and establishing who and where the inventor is critical in determining inventorship and ownership. So I'm going to talk not at all about inventions that are conceived and tested in space, such as those on the International Space Station, but rather I will speak about inventions that are conceived on Earth and tested or validated in microgravity environments, such as the Tumbleweed platform. So it's more usual that either the hypothesis will be formed on Earth, the experiment designed, launched into space, and results will be obtained in the microgravity environment, or results will be obtained in the microgravity environment and then they will be interpreted on Earth, and these will be used to formulate an inventive concept. So in both cases, in my view, it's clear that the intellectual step occurs on Earth. The actual devising, according to UK law, or the conceiving, according to US law, of the invention is definitely a terrestrial activity. So I think that that is very helpful in making commercial agreements between parties which will benefit from such research. So as I mentioned, because we have this legal lacuna in legislation governing intellectual property in outer space, contracts do tend to do a lot of the heavy lifting. In particular, the usual issues such as ownership, improvements and derivative work, data rights and confidentiality, and the jurisdiction will be covered in such contracts. And I think the data rights needs particular addressing, because it's a separable issue where the invention was made and by whom, and the rights to access the data generated as the result of the microgravity research are separable to a certain extent. So those need to be covered off in the contract. Another interesting issue is sufficiency and enablement. So, as you are probably aware, it is a fundamental part of the patent quid pro quo that full disclosure enabling the skilled person to work the invention armed with his common general knowledge and the information available in the specification is given, yeah, and that is a fundamental point of patent law. And in the case of microgravity enabled inventions, these often exhibit properties that cannot be reproduced under terrestrial conditions. So how do we square that off when the skilled person is not in a position to reproduce the exact conditions? So thinking from a European perspective, I think that in the case of microgravity inventions, the burden is going to be quite high on substantiating um, the fact that the invention has indeed been made. So the plausibility burden is likely to be very high, and the requirements for supporting evidence are going to be correspondingly high. And in Europe, once a patent is granted, it has a presumption of sufficiency, and the burden of proof is on someone challenging that to prove his case. So I think that at least the European Patent Office is going to be very strict in the evidential burden for someone seeking a microgravity implemented invention. So uh, all possible parameters need to be included, such as microgravity thresholds, radiation exposure, thermal cycling, mission duration, any technical details that would enable the person, were they in a position to reproduce the experiment, to do so. Novelty and obviousness are also universal requirements for a patentable invention. And I think there are a couple of issues that are going to arise with microgravity implemented or discovered inventions. So in the case of composition of matter claims for a substance or a formulation, for example, these must be qualitatively different from compositions made at a terrestrial gravitational conditions. So the substance needs to be new without wishing to state the obvious. So just because a substance has been produced in microgravity, it does not automatically mean it's new if it's identical to a substance that has been produced on Earth. In the case of process claims, you can imagine that a claim including a process step wherein the process is conducted in a microgravity environment would be formally novel if that has not been undertaken previously. But all inventions must fulfill the requirement of inventive step and represent a non-obvious solution to a technical problem, which cannot be conducting the process or making the material in space. It needs to solve an actual technical problem. So as in the case of Keytruda, the technical problem was the provision of a subcutaneous formulation rather than an intravenous formulation. So these are the kind of issues that patent attorneys will need to take into account when constructing applications directed to these technologies. When any new field emerges, there is always a stampede of people who try and obtain broad claims covering enabling technologies or core technologies in the area to try and get a chokehold on the field. So this happened during the dot-com boom. It happened when gene sequencing was first made a realistic possibility. And there is some evidence that broad claims are already being granted. So having a quick look, people are obtaining broad claims to drug crystallization under microgravity conditions. There's a bit more to the claim than that, but you can see that this could prove a serious obstacle for people conducting subsequent research in that field. So that's something to be aware of, and it'll be interesting to see how the courts deal with these type of situations. So a very rapid overview of what I see as being the core issues of intellectual property that you need to address when you're planning research using microgravity. As we've heard from Johanna's talk and the example that I gave, microgravity is a unique environment enabling unique patentable inventions. The territorial IP rules that exist on planet Earth do not map cleanly onto space, and they need careful consideration. Contracts are presently being used to fulfill the legal gap. I think there are untested issues of sufficiency, and again, the best advice is to provide as much technical detail as possible because the burden of plausibility is likely to be very high at the European Patent Office. And we're expecting a rapid legal development as space R&D and manufacturing scales. So that's really all I wanted to say, and we will have some time for Q&A now. I'll see if anyone has put questions in the chat. Here we go. Q&A. So Maria Casanovas Crespo asks, what's the current mission duration time of microgravity for the experiment? So I think that's one for you, Johanna.
So yeah, it depends a little bit on what you need, as always, right? So there's obviously levels of microgravity, and depending on that, like there's also multiple options for you. So for example, for a biological payload, you could, for example, even use a machine that simulates microgravity on Earth. So there you kind of like it twists and turns. There's multiple mechanisms like random positioning machines or clinostats that kind of do a net zero gravity over time, basically. So there's this option to get like a longer exposure of net zero. On the other hand, you could, for example, drop something from a like drop tower. There's one in Bremen, for example. There you get like a couple seconds each drop. So think like 3 to 5 seconds. There you usually get a bit better free fall already. And then, yeah, after that, you start flying. So first of all, there's like the parabolic flights with the plane, right? So there per parabol, usually there's like 15 on a flight, and per parabol, you get like 30 seconds of microgravity. So there you're getting into like some cool territory already. And then you start with the rockets. So there's, for example, sounding rockets that just go barely to space and back down. So doing one parabol. They're at a couple minutes. So for a lot of experiments, that often is enough already. And only after that, like you obviously don't have to go through every step, but only after that, there's like the orbital where you get like the really longer durations. Our flight, for example, will be like 2 to 12 weeks. We're currently tending more to 12 weeks, but like in the scaled mission, we see that there's like quite different requirements at the moment. And we really have experiments on board that take from a couple of minutes to a couple of days or even weeks. So like there's a bit of a for the Oasis plan in 2 months, it's not coming back, right? So theoretically, the satellite, like it's a 300 CubeSat, it will orbit for like until it kind of solves on the atmosphere, like burns up, right? So that's a couple years still, but we're first, yeah, the experiments itself are just going to take a couple of weeks. For the second mission, for the first return mission, that's the 2 to 12 weeks that I mentioned. So that's kind of where we're at there.
Great. Thanks a lot. So Andy Clempson asks, contracts provide most clarity about ownership of IP created in space. However, this would not help in the context of infringement. Is it possible to infringe a UK patent by carrying out microgravity research manufacturing on a spacecraft which is registered in the UK or which has just launched from the UK? So I will have a stab at this one. So the guidance that we have is from the Outer Space Treaty, and I think UK law courts would also follow the reasoning of the Federal Circuit and draw an analogy between the situation on the high seas. And I am more or less convinced that a UK patent could potentially be infringed if the launch and registration was in the UK. But we don't know. Have you got any thoughts about that, Johanna?
I was wondering if the launch location matters as much because usually like rockets fly under a flag, right? So for example, our spacecraft is gonna fly under an Austrian flag, even though it's launched out of California. So I was wondering if there's a difference between registration or launch location.
Interesting. I'm using interesting to say that I don't know. um, Anonymous attendee, what if the patent is being used for Earth application? Does the territorial IP rules applies in relation to the market access? So I think that's easier. So once the invention has been made and a terrestrial patent is applied for, then the normal rules would apply. So let's say the new formulation of Keytruda was developed using research in outer space, and the patent was filed in the normal way, and protection was obtained in various jurisdictions. The usual rules would apply to that. So I had a couple of questions, if you don't mind. Could you give us an example? So you've got various size boxes, for example, the nano, the mini, I can't remember what the big ones are called. But could you give us examples of experiments that can be conducted in those?
Yeah, I mean, I can tell you what's on our first mission. We have four customers on board, and there an example is a software payload that is literally just sending up and down data from TU Delft, where they're basically figuring out a new navigation system inter alia for satellites. And doing this with like a machine learning model that is usually powered by a quantum computer, but now testing it if they can do it with a like much smaller in a like much smaller way on like a satellite. So that is, for example, one thing. But then we also have like some material studies, and we have a startup on board that is sending a microfluidic chip to study protein crystallization, for example.
And that's on the nano.
No, like the for a first mission, they're sized a bit differently. Yeah, but it's a bit bigger than a nano what they have there in terms of volume. For the larger ones, there's obviously a lot more options, especially with cells, and in terms of instrumentation, of course. Like a lot of it is like building in also like, you know, optical sensors, for example, or measuring devices that you can send data up and down with. Yeah, and sometimes it's also about quantity, especially if you're thinking in the direction of production, right? So for example, could do like a bigger bioreactor or something like that to have more protein crystals afterwards. So there you really start scaling, or for example, the CBLAN fibers, they're also like the machines are like this size basically. So
Yeah, yeah.
suitcase sized
Big
or
one
large.
is like 8 kilos, right?
Yeah, that's the ones that we're offering in the like standardized format, obviously. Like if you ask us there is quite a bit of size to go up. I think the real limit is at about 20 kilos. So
So
yeah.
okay, could I say my cat?
I mean, yes, but I don't think it would be very nice to the camera.
It's quite an experience, right? Um, so which launch platform are you using with your first mission?
Yeah, so for the first one, we're going with the US. So there's rideshare platforms with SpaceX. At least there's still rideshare platforms with SpaceX. And then with the second one, we kind of want to go to Europe and have a bit more specialized launches, grow with the industry here as well. Um, there's you were talking about the patenting, but even beyond that, there's like a bunch of funny legal situations you get yourself into. I recently was asked what the country of origin is if you return something from space for export regulations. So having something that is a bit more local is always beneficial. Let's put it like that.
Yeah. And the experiments you're describing, so the microfluidics and crystallization, there is the possibility of monitoring those from Earth. Yeah.
Exactly. Not just monitoring, you can also send data up. So for example, if you have your model running and it's doing something, you could even give it an impulse to do something else. It will send you down telemetry data. If you want, for the first mission, that's all we're doing, you can even just get the pictures and use that as the data you get back. So even during the mission, you have something to go off on and have a feeling on, or maybe course correct if there's something wrong. Yeah. So
Yeah.
there's a bunch of options.
Okay. Cool. And the first launch is in July in California, you said.
Yeah, we're not really allowed to say it because there's always a bad cloud that could be in front of like that could be messing with the launch dates. But yeah, some like in summer is
Oh,
always.
okay. It's like bad luck, like yeah, mentioning Macbeth in a theater or something.
Yeah, no, I'm not sure if it's bad luck, but it's yeah, it's just a thing where people don't wanna um, have to like you'd rather not say something before you can't complete on it, right?
Yeah. No, sure. Well, that was excellent. Thank you very much for a great presentation, Johanna. I think there has been a lot of interest from the audience. So we will be, I have been recording this. So once I've zhuzhed it up a bit, I will send a link to the recording to participants. And Johanna and I are going to produce a short article as well. And if you would like a copy of that, I will gladly send it out to you. So even though in on the uh, ether we cannot hear people's thunderous applause, I'm sure it is happening right now. So thank you very much, Johanna, and thank you for your kind attention. And we look forward to seeing you at our next event.
Yes, thank you so much, Adrian, also for the research and the organization. Thank
No
you.
problem. You're welcome. Bye. Bye.
Bye.